Hello, everybody. Welcome back to class. I'm glad you all made it. Found your way here. Let me know who's in the chat. Navik's in the chat. Good to see you, Navik. You don't miss a class. Reagan, Max, Akil. James says hello at Navik. Good morning, Jax. Jared, Inman, good to see you. You guys picked a good class to come to because we're doing some awesome problems today. Hello, Will. Good to see you. We'll get started in, I don't know, 90 seconds or so. If anybody has anything interesting they want to share to the chat, share it. You know, we're all listening. Hello, Logan. I'm trying a new flavor creamer in my coffee this morning. I don't drink coffee with creamer. I go just black for the coffee. All right, so it's 10 o'clock. We can get started. Black coffee all the way. Yeah, it's the best. It's hard to mess up, and it's good. So, all right, you can see this. I'll put it. It's coffee and water right there. Just coffee beans and water. That's all it is. Okay, enough of that. We got to focus. All right, let's do the simultaneous sip, and then we could get on to doing some definite integrals. All right. All right, let me see in the chat who sipped, who didn't sip, and also I want to see, he's got tea. Navik's got tea. That's fine. I want to see, how are you watching the stream? Laptop, phone, tablet, TV? Any of you stream this to the TV? That'd be pretty cool. Laptop. All right, seems like laptop's the best way to watch and chat, I would imagine. Big screen, surround sound, sweet. Computer. Laptop, phone. Cool. Glad to see we've made it onto some phones. Okay, well, so let's just recall that the integral from a to b of f of x dx is equal to the sum, no, it's not, is equal to the limit as n goes to infinity of the sum from I equals 1 to n of f of x sub I delta x. Okay, so this integral, this definite integral is really the limit of a sum. Okay, so that's important, especially in these first few examples. Let's talk about how do we evaluate integrals. And I should say before we get into writing down some of these results, those of you who have taken calculus before are going to want to use your shortcuts that will eventually learn, but those aren't going to work on a test or a quiz. Okay, so we have to learn how to do this, using the limit of a sum first, and then eventually we'll get to our shortcuts. Okay, so those of you who know how to evaluate integrals the fast way, that's a good way to check your answer, but it's not going to get you any points on a test or a quiz. Okay, so keep that in mind. Okay, so let's talk about how we're going to first evaluate integrals. So the following identities, let's see, will this be on this week's quiz? Yeah, let's lock it in. We'll do some sort of evaluating, either approximating an integral or actually evaluating the integral will be what's on the quiz. But I'll put that in an email this afternoon. So yeah, these types of questions that we're doing today will be good practice for the quiz. And it's also good because I have a million YouTube videos that talks about how to do these. So there's a lot of resources. So the following identities are helpful in evaluating integrals. And Lauren, that was my plan the whole time. So it's not, I don't mean to throw you under the bus for asking. The plan was for this to be on the quiz the whole time. Okay, so here's some identities. The first one is that the sum from I equals 1 to n of the function I. Okay, so if you just add up the first n integers, 1 plus 2 plus 3 plus 4, all the way up to n, that's the same thing as n times n plus 1 over 2. Okay, so if you want to add up the first 10 numbers, 1 plus 2 plus 3 all the way up to 10, that's the same thing as 10 times 11 over 2. So it's 55. It's a quick way to compute those sums. Similarly, the sum of the first n squares, so 1 plus 4 plus 9 plus 16 and so forth, is n times n plus 1 times 2n plus 1 all over 6. Okay, and if you're interested, and there's one last one we'll write. If you're interested in why these identities hold, you should either take combinatorics, which would be a class you'd take in a few years if you go on the math direction, or you could take discrete math, which you could probably take after Calc 2. So the last one is the sum of the first n cubes. So 1 plus 8 plus 27 plus 64 plus 125 and so forth. That's n squared times n plus 1 squared all over 4. Okay, so these are 3 identities about sums. Next, we could state some other identities. Sum from I equals 1 to n of a constant. Okay, so if you add a constant to itself over and over again, n times, well, that's the same thing as multiplying by the number n. Right? Like, let's say c was equal to 5. 5 plus 5 plus 5 plus 5 plus 5 plus 5 n times is the same thing as n times 5. Okay, so if you have a constant times some sequence that's being added up, you could pull out the constant. You could break up a sum in terms of each of its components, deal with them one at a time. And then last, you could break up a difference. Okay? So this is saying, hopefully these will become clear. Basically, this is saying if you add up a bunch of numbers, it doesn't matter which order you add them up in. Okay, that's what this represents. And then again, if you add some numbers and then subtract some numbers, you can figure out, you can add up all the positive numbers, add up all the negative numbers, and then take the difference. Let's take a look at an example to see that this really is not all that crazy. But these three are the big ones that we'll use the most. Maybe D as well. A, B, C, and D are probably the ones that are the most useful for us. So the question is, evaluate the Riemann sum for the function f of x equals x to the third minus 6x taking the sample points to be right endpoints. A equals 0, B equals 3, and n equals 6. Okay, so what was the Riemann sum? I don't know if I actually defined what a Riemann sum is, but it's this part. So ignoring the limit, this part here, this is a Riemann sum. Right, it's how we approximated the area under the curve. Okay, so I'll work through this together with you, just so we can see that maybe this is not as bad as we think it is. There's a part B to this example, but we'll write it down after we do part A. So basically what we want to do is figure out what the right endpoints are. So we'll take our number line, which goes from 0 to 3. Again, slow me down if we're going too fast. We'll take our number line, which goes from 0 to 3, and we'll break it up into 6 sub regions, subintervals. of equal width and our sample points are the right endpoints. I guess we should first say, how wide are they all? Well, we call it delta x. How wide are each of these subintervals? How long are they? Regions, which is n. So in this case, it's 3/6. So this first endpoint is in the location 0 plus 1/2, which is 1/2. The next one is 1. The next one is 3/2. The next one is 2, 5/2, 3. Right, so I started at 0 and I just kept adding 1/2 to it to get to each to get to the next endpoint. 1/2, 2/2, 3/2, 4/2, 5/2, 6/2. Okay, so what we want to do is we want to evaluate the sum from I equals 1 to 6 in this case. Okay? So really this is equal to f of 0.5 plus, because that's the first right endpoint, plus f of 1 plus f of 1.5 plus f of 2 plus f of 2.5 all times delta x, which we said was 1/2. Okay, I'm going to pause here. Please ask any questions if you need anything clarified. Each region has width 1/2, so I can factor out the 1/2. And now what this is saying, add up the function evaluated at each of the right endpoints. The first right endpoint is 1/2. The next right endpoint is 1. The next right endpoint is 3/2, then 2, then 5/2, then 3. We need to evaluate our function, which we haven't even looked at yet. This whole question so far is how we would do it in general with no function given to us. We're eventually going to use this function. Okay, and then we're going to add all these up, and it's just going to give us a number. Okay, and that's going to be our answer. Okay, so we would then want to evaluate our function at each of these endpoints. So we would plug 0.5 in for x here, and that's going to give us some number. Okay? Similarly, we'll plug 1 in, it'll give us another number. 1.5 will give us a number. Don't you have to multiply the values by 1/2? Yeah, I put a 1/2 on the outside. I would have preferred to put it here, but I ran out of space. So the 1/2 is here. So yeah, this was the delta x. Right, so you would use a calculator. I mean, ideally, you would have a computer do this for you to evaluate the function at each of these 6 points. So for instance, I'm not going to go through them all, but like f of 0.5 would be 0.5 to the third minus 6 times 0.5. Which is negative 2.875. Okay, and you could go through all of these to compute them. Then you would add all of these up and then multiply by delta x, which is 1/2. And it works out to be negative 3.9375. Okay, and so what is this? This is an approximation for the integral from 0 to 3 of x to the third minus 6x dx. Okay? Well, the next part of the question, I hope you had these identities written down because we're going to use them. The next part of the question wants us to actually evaluate the integral. Does anybody have any ideas of how we're going to evaluate this integral? Well, I'll get started. If you have any ideas, feel free to share them. All right, so we know use the summation identities. Yes, exactly. Okay, hey, Max, easy with the spoilers here. We don't know about the fundamental theorem of calculus yet, okay? So maybe one day, but for now, we don't know. There's no connection in my mind, right? How are integrals, which is the area under the curve, related to antiderivatives? I don't know. Okay, so yeah, we should use some summation identities because we do know that a definite integral is the limit of a sum. So we know that the integral from 0 to 3 of x to the third minus 6x dx is equal to the limit as n goes to infinity of the sum from I equals 1 to infinity of f of x of I delta x. I have a funny feeling. No, it's not a problem, Max. I expected people to give that answer. Unfortunately, we got to go through the brutal method first. Yeah, so we want to evaluate this limit, and we're experts. We are experts at evaluating limits. We spent a lot of time at the beginning of the semester doing this. Okay, so what we need, what bits of information do we need? We need delta x, and we need x sub I. We already know f. It was given to us. Okay, so again, we'll do the same thing as we did before. We'll take our number line. And we'll break it up into n rectangles, n being a large number. Okay, So, ideally, we're going to break it up to infinity many. So we need to find delta x. Delta x is equal to b minus a over n. We need a little bit more space. Which in our case is 3 minus 0 over n. Okay? So our first right endpoint, and again, we'll use right endpoints. It doesn't matter which endpoints we use, but it works out easiest when we use right endpoints, in my opinion. Our first right endpoint would be 0 plus 3 over n, which is 3 over n. To get to the next right endpoint, we have to add another delta x. So that's 3 over n plus 3 over n, which is 6 over n. To get to the next one, we go to 9 over n, and so forth. So our first right endpoint is 3 over n. Our next one is 6 over n. Our ith right endpoint is what? The first one is 3 over n. The second one is 6 over n. The third one is 9 over n. The ith one would be 3i over n. Yeah. And in general, so for your notes, x sub I is equal to a plus I delta x. Okay, so this is how you would check your answer in general if you can't see a pattern. A is 0, I is just going to be I, and then delta x we already found is 3 over n. Okay, so our integral is equal to, well, we have all the information we need to start evaluating this integral. It's equal to the limit as n goes to infinity of the sum from I equals 1 to n of f of x sub I times 3 over n. Okay, we could use e, this identity e, to factor out this 3 over n. That's just a constant. Right, so I evaluated our function at 3i over n, which is 3i over n to the third minus 6 times 3i over n. And we want to evaluate this limit. Okay, if we can evaluate this limit, we're done. We get the answer. Okay, so this is equal to the limit as n goes to infinity. Again, we have a 3 over n. Sum from I equals 1 to n. A 3i over n to the third is 27 I to the third over n to the third minus 18 I over n. And we could use one of our identities to break up this sum. And now we could factor out the constants, right? 27 over n to the third is just a constant. 18 over n is also just a constant. So this is equal to the limit as n goes to infinity of 81 over n to the fourth I to the third. A sum from I equals 1 to n of I to the third minus 54 over n squared, sum from I equals 1 to n of I. Okay, I know we've been going, this probably is a little bit fast, so please ask any questions you may have. And I have a question for you. Where do we go from here? Where did the 81 and the 54 come from? I factored out 27 over n to the third. So it became 3 times 27 is 81. And then similarly with this sum, I factored out the 18 over n. So it's 54 over n squared, right? 3 times 18 is 54. Okay, so how do we go from here? Well, we have an identity. We have an identity that tells us how to express the sum of the first n cubes. And similarly, we know how to add the sum of the first n numbers. So we're going to use 2 of the identities. So instead of having the sum from I equals 1 to n of I to the third, we could use the identity and replace that with n squared times n plus 1 squared over 4. And we can replace the sum from I equals 1 to n of I with n times n plus 1 over 2. Right? These are 2 of the identities that we stated at the beginning of class. Okay? This here is something we definitely know how to evaluate. Right? I mean, we usually see it with x's, or we did when we were first talking about horizontal asymptotes. But this is just a rational function This is just a rational function where the degree of the numerator is n to the fourth. So the degree of the numerator is 4, and the degree of the denominator is also 4. We could just divide their coefficients. So this limit becomes 81 fourths. And similarly here, this is a rational function. The degree of the numerator is 2. The degree of the denominator is also 2. So when we take the limit as n goes to infinity, we just look at their leading coefficients. And now we can express this as negative 6.75. So the integral from 0 to 3 of x to the third minus 6x squared minus 6x is negative 6.75. Are you all silent because you are awed by the beauty of this example? Or are you silent because the chat is broken? Or are you silent because you're confused? Because I could go through the steps again if you'd like. Master Toru just joined, so he'd probably be a little bit lost. Silent and amazed. That's great. That is great. Yeah, so this identity here, I'm gonna if you're asked to use those 3 identities on a test, I'll provide those to you. Okay, but you should know how to use them. Like replacing, if I just tell you that the sum from I equals 1 to n of I to the third is equal to this, you should know how and when to use it. All right, well, if nobody has any comments, we could take a look at another example. So express the integral from 2 to 5 of x to the fourth dx as a limit of sums. Okay, so we want to express the integral from 2 to 5 of x to the fourth dx in this form. All right, I'll just kind of talk through how we should do this. But again, I encourage your feedback. So no identities needed for this one. Correct. Yeah, we're just going to express it in this form. So we would get it to here, and then we would stop. We're not going to actually evaluate it. We're just going to get to this point, and then we'll stop. So what bits of information do we need? We need delta x, and we need x sub I. And that's it, right? Because we were given the function. Should be an n here, but It's not really important. We were given the function. So we need x sub I, and we need delta x. Okay, so what's delta x? Well, delta x is b minus a over n. So again, it's 5 minus 2 over n, which is, just by chance, 3 over n. Yeah, good, Bella. And x sub I is a plus I delta x. Okay, so x sub I is equal to 2 plus 3i over n. And just for completeness, f of x sub I is equal to, well, this thing to the fourth. No, it is not the imaginary number. We just use it to index which region we're in. So this would be like I equals 1, I equals 2, I equals 3, and so forth. Some people use J to avoid that confusion, but I use I. Okay, and now we're done. So we know that the integral from 2 to 5 of x to the fourth dx is equal to the limit as n goes to infinity of the sum from I equals 1 to n of 2 plus 3i over n raised to the fourth times delta x. Right, and so then the challenge, which we don't have to do for this example, then the challenge would be trying to evaluate this limit. And you could imagine you'd have to multiply it out 4 times and use a number of identities, some of which we haven't even mentioned in that list. So this would get pretty messy pretty quick. Why did we not have to use a in the previous example? Well, we did. Yeah, you're right. It's because a equals 0, right? A was 0 in this example. Okay. Let's look at 2 more examples simultaneously. So evaluate the following integrals. By interpreting each in terms of areas. Okay, so the first one is the integral from 0 to 3 of x minus 1 dx. And the second one is the integral from 0 to 1 of the square root of 1 minus x squared dx. Okay, so what we want to do is sketch the region, find the area that's above the x-axis, find the area that's below the x-axis, just using your geometry techniques. Okay, so I'll give you, let's say, 2 minutes to get started on this, and then I'll finish it up for you. But I particularly like this question, part B, because those of you who know all the shortcuts from AP Calc, well, you don't learn how to do this integral, so that's how I like to stump you guys. Unless you do, and then I'll have to just come up with harder questions. All right, so I'll give you 2 minutes. Please ask any questions you have in the chat. But again, try to sketch what this region looks like, and then find the areas. What's an arctrigo? I'm not sure. I've never heard that before. Okay, that has not been 2 minutes. I'll give you 30 more seconds. Arctrigo. Arc cosine, arc san, arc tan. I don't know what you call those. Oh, arc trig functions. It's like the inverse of a trig function. A trig function will take an angle and give you a ratio. The inverse will go ratio to angle. Okay, so let's start with A. So this region, let's draw it in the xy plane. Also, I don't know if you guys noticed, but I only use blue markers because they show up best on camera. And these are my last 2 blue markers. So it's going to be interesting next week. I might have to try to sneak onto campus to steal some, but don't tell anyone that. Well, not steal. I mean, I have access to them, but I might have to sneak onto campus to get them. Okay. So we want to graph the curve y equals x minus 1, and that's a line with slope 1 that has a x-intercept of -1. And we go from 0 to 3. Okay? And so we want to find the area of this triangle and find the area of this triangle. Okay, and so the integral, the area of this triangle, this is a triangle with height 1 and length 1. The area of this triangle is 1/2. And the area of this triangle has height 2 and length 2. So it has area 2. So this integral is equal to the positive area, which is 2, minus the negative area, which is 1/2. Okay, and then for the other one, we want to sketch this curve. What does the curve y equals the square root of 1 minus x squared look like? That's a semicircle with radius 1. but we're only going from x equals 0 to 1. So we want to find the area of this quarter circle. And so the integral from 0 to 1 of the square root of 1 minus x squared dx is equal to the 1/4 of the area of a whole circle with radius 1. The area of a circle with radius 1 is pi times 1 squared, which is pi. And 1/4 of it is we divide by 4. So we get pi over 4. All right, well, I'll hang around and answer any questions you may have, but I basically took you to the end of class. Remember, you got to smash the like button before you get out of here. It's so important. It leads to higher test scores, so they say. But yeah, if you have any questions about these questions or anything we've done today, I'll answer them in the chat. Thank you, Max. Yeah, Max, see if you can solve this with your antiderivatives. It's going to be a tough one. Turner knows the appropriate way to leave a class. Navik, yes, smash the like button as hard as you can. That's a good attitude. Could you explain B again? Yeah. So we want to find basically the region bounded by the curve y equals the square root of 1 minus x squared. Let me get out of the light. I got my spotlight down there. We want to find the region that's bounded by the curve y equals the square root of 1 minus x squared, which is a semicircle. The whole curve would be a semicircle, but our x bounds go between 0 and 1. Okay, so like the whole curve y equals the square root of 1 minus x squared would look like this. But we only care about x going from 0 to 1, so it's just the right half of the semicircle. And the area of the entire circle is pi, right? It has radius 1, so the area of the whole circle would be pi. We're looking for the area of just 1/4 of it. And so that's pi over 4. Did that answer your question, or did that help? What level of math is this never seen integrals rep with the sigma notation before? I know that it's sum of small rectangles. Cool. This is just Calc 1. Yeah, so if you take AP Calc, you should see this, and or if you just take calculus in college. Yeah, this is how you do integrals, and when you do applications in a physics class, you would typically set it up with a sum instead of, and then you hope it becomes something we could integrate. Okay. I'm 2 minutes past time to end class, so I'm out of here. Bye-bye.